Hello everyone, and welcome back to Physics-Based Animation. In the last video, we learned all about how to implement a fully implicit time integrator for stable finite element simulation. We also learned how to make our simulations a bit more visually impressive by skinning them with a high-resolution surface mesh. We've come a long way since our one-dimensional mass spring system in the first video, and in this video we're going to switch gears, moving away from the volumetric elastica we've been focusing on to talk about one of the major success stories of physics-based animation. Cloth simulation. Here we can see some simulated examples of a variety of different cloth squares. Our goal is to adapt the things we've learned so far about physics-based animation to concoct our very own cloth simulator. And to do this, we're going to rely on the venerable finite element method, the very same one we used to simulate bunnies and armadillos in the previous video. But we'll see there are some important differences we'll need to address to keep our virtual characters at the forefront of haute couture. To begin, let's remind ourselves how finite element methods worked when applied to volumetric objects. Recall that the initial step in the method was to divide the volume of our object into small subvolumes. And we chose tetrahedra to represent these subvolumes. From this choice arose one particular brand of finite element method. Even though cloth is technically volumetric, it is often modeled as a surface, using something like this triangle mesh. Practically, that means our geometric representation doesn't give us a volume to divide. This means we can't fall back on the familiar tetrahedral finite element method. Fortunately, there's an obvious choice of element type to build a new method around. And that's a triangle. This is particularly convenient because oftentimes we can use the input cloth mesh as the simulation mesh directly. Our basic setup is going to mirror the tetrahedral case. Our element will be a triangle comprised of 3 vertices and the area it encompasses. Because a triangle is fundamentally a 2D shape, I've embedded it here in a 2D coordinate system given by capital X and capital Y. Remember that a fundamental part of the tetrahedral finite element method was establishing a mapping between the undeformed and deformed shape of a tetrahedron. It was this mapping that ultimately allowed us to measure potential energy, kinetic energy, and simulate deformable elastic objects. Well, the game hasn't changed. We have to do the same thing here, creating a mapping between our 2-dimensional triangular element and its 3D state in the world. Hopefully you have some intuition that if we can do this, the rest of the variational mechanics framework will fall into place. We're going to make an important conceit right off the bat. Rather than treat our triangle as belonging to a 2D reference space mapped into a 3D world, we are instead going to bring back the third reference space dimension. We will see later that this will eventually let us reuse ideas from volumetric finite element method, which is quite convenient. There's an argument to be made that this is really the correct way to model cloth. As I mentioned before, cloth isn't really a 2D construct. Rather, it's a thin volumetric sheet. It's easier to demonstrate in this rotated view. Our triangle mesh really represents the medial surface of a thin prism of cloth. This view takes us back to the volumetric perspective of the previous 2 lectures, but without requiring a volumetric discretization. Now our job is to find a mapping between these 2 3-dimensional spaces, something that we've succeeded at previously and hopefully will succeed at again. For tetrahedral finite element method, we accomplished this by figuring out how to rebuild functions inside of a tetrahedral element from just values stored on the vertices. One thing I want to stress is that the finite element approach is really a recipe, and this is just the first step of that recipe. So let's see if we can apply it to cloth simulation. Here's our setup, and it looks very similar to what we've been working with in the previous videos. We have our triangular element embedded in a 3D reference space, And just as before, we'll represent a point in this space using capital X. We'll store function values at the vertices of our triangle, and we'll rebuild the function inside the triangle using a weighted combination of these per-vertex function values, multiplied by per-vertex interpolating functions called shape functions. As we did for a tetrahedron, we can now try and derive a formula for our shape functions. And as before, we will need to introduce the constraint that all our shape functions sum to 1 in order to be able to make any progress. We can enforce this by expressing our first shape function, phi sub 0, in terms of the other two shape functions, phi sub 1 and phi sub 2. Now we just keep following the recipe. So given the reference coordinates of our triangle vertices, we will build phi such that they exactly recreate the reference coordinate of points inside our triangular element. This all seems well and good, but let's pause here to consider something. The cloth we are trying to simulate is a volumetric construct, and our triangle just represents one small part of that. At some point, we are going to want information that lies off of this surface. This means that we will also need our function reconstruction to handle points that are slightly offset from the triangle surface gracefully. This complication is the major difference between the volumetric finite element methods we've seen before and the triangular finite element methods we're working on now. The current problem setup is going to make it difficult to exactly solve our equation for the phi functions, so we'll have to get a little creative. Rather than try to reconstruct the reference coordinates of points off of the triangle, we'll aim to reconstruct the reference coordinates of the nearest point on the triangle itself. Mathematically, this means we are giving up on exactly solving our shape function equation, and instead rephrasing it as an optimization problem, the goal of which is to find the shape function values that minimize the error in the reference coordinate reconstruction. Here, we can use a sum of squares objective function, which makes this minimization quadratic in phi. We should be able to solve a linear system to get the right answer. And here's what that looks like. As is becoming a trend, you should see some similarity between this formula and that of our tetrahedral finite element. The main difference is that for triangular elements, we solve for the shape functions phi sub 0, phi sub 1, and phi sub 2 in a least square sense, while in the tetrahedral case, we could just solve for the shape functions exactly. What we are really computing are the barycentric coordinates for the projection of our point onto the triangle. When our point is on the triangle, we get its exact barycentric coordinates, which is what one would hope would happen. This is all well and good, but it's a little bit painful that we can't satisfy this equation exactly. Just to be sure that's the case, let's explore a bit more. Maybe we can do a little bit better. One of the nifty things about least squares optimization is that any error in the solution will be orthogonal to our triangle. This means that there is some distance alpha which we can travel along the unit normal vector capital N to exactly recover our reference coordinate. If we can compute alpha properly, we can just add this information back into the result of our optimization. If we reconstruct the vector capital X minus capital X sub 0, we can see that our alpha is the length of its component orthogonal, normal, to the triangle. We can compute this length by projecting capital X minus capital X sub 0 back onto the normal, which we can do using the graphicist's favorite operation, the dot product. And now we know how to exactly reconstruct our reference coordinates using our shape functions, and a little geometric information, the unit normal vector to the triangle. This reconstruction is still linear in capital X because the triangle surface normal is constant. It doesn't change no matter where you go inside the triangle. Now what remains is to leverage all of this to build our mapping into the world space. It's immediately clear that for a point on our triangle, our barycentric shape functions can be used as before to reconstruct its world space position. However, this will fail for a point off of the surface. How can we correctly apply this offset in the world space? Well, one can reasonably approach this by offsetting our projected point in the world space by the same amount, but along the world space triangle normal n. We can encode this by adding alpha times n to our world space mapping equation, which completes our shape function derivation. Note that, like the undeformed normal, capital N, the deformed normal is constant across the triangle, and so this whole thing is still linear in capital X. That will be very helpful when we start computing deformation gradients, which is going to happen in a bit. After all that, we can finally begin turning our variational mechanics crank, and we'll start by identifying our generalized coordinate. As usual, we'll choose this to be the stacked vector of per-vertex world space positions. Now you might wonder what's going on with the world space normal, but we'll see later that this can be recomputed from just these world space vertex positions, so we really don't need any more information. Following the standard approach, we can now define our generalized velocity as the stacked vector of per-vertex velocities. And we can use these velocities to compute the kinetic energy of our cloth triangle. Here we integrate over the cloth domain represented by our finite element, which includes the volumetric thickness of the material. However, because the cloth is so thin, we can assume that the kinetic energy is effectively constant in the direction orthogonal to the triangle, and this allows us to rephrase our integral as the integral of kinetic energy over our triangle times the thickness of the cloth itself. Using our generalized velocities and shape functions, we can arrive at a formula for the kinetic energy of a single triangle, which includes our per-triangle mass matrix. This is very similar to the tetrahedral case and can be integrated using the same technique from the fourth video. Next, we need to extend this from a single triangle to a full piece of cloth. For that, we need the generalized coordinate of our cloth. And again, we will use a stacked vector of per-vertex world space positions for this. Similarly, our generalized velocity will be the stacked vector of per-vertex velocities. And we will formulate the cloth kinetic energy as a sum of per-triangle kinetic energies, where we use element selection matrices to connect our global generalized coordinate to our per-element computation. This gives us our cloth mass matrix M, and M can be constructed via assembly, very much as it was for tetrahedral finite element methods. Now we can move on to figuring out the potential energy for a piece of cloth, and once we have that, we can start figuring out the equations of motion. Again, we're just going to follow what is becoming our standard approach, and we'll start by working it out for a single cloth triangle. Just as for tetrahedral finite elements, we will build our potential energy function around the deformation gradient. Remember that the deformation gradient is a matrix which stores the derivative of the world space position of a point with respect to its reference position. If you need a refresher on this, please see the fourth video in this series. Here's the formula for the world space mapping for a single triangle. And with a bit of rearranging, we can rewrite it in this form. Here we can clearly see the world space normal n and the reference space normal capital N standing in for the fourth vertex and fourth shape function that was present in the tetrahedral case. In this form, we clearly see that our world space coordinate x is linear in the reference coordinate capital X. Taking the derivative with respect to capital X gives us an explicit formula for the deformation gradient, which is actually pretty elegant. The linearity of the world space mapping with respect to capital X means that this deformation gradient has the nice property of being constant inside a triangle. We can compress the notation a bit more by noting that a large portion of our second matrix is really just the gradient of our shape functions with respect to the reference coordinates. Next, we introduce our material model in the form of the strain energy density function psi, and compute potential energy by integrating over the volumetric cloth domain. Once again, we assume that because the cloth is very thin in one direction, that the strain energy density can be considered constant in that direction, which allows us to simplify our integral to an integration over the triangle itself, multiplied by the cloth thickness, h. One of the advantages of using a 3D reference space formulation for our cloth simulation is that we retain a 3x3 deformation gradient. This is because we are still mapping from a 3D reference space to a 3D world space. As a consequence, we can directly use standard strain energy density functions in our cloth simulation, like the Neo-Hookean energy we used for volumetric simulations in the 4th and 5th videos. For the simulation of cloth, we are going to introduce a different type of material model that is also very popular in computer graphics. But to do that, we are going to revisit the concept of deformation. In previous videos, we used the difference in reference and deformed squared lengths to characterize the amount of strain an object was under, and we showed that this could be expressed using the deformation gradient. In particular, we developed a specific strain measure, the Green-Lagrange strain, which measured deformation using the right Cauchy-Green deformation tensor. Let's take a closer look at this deformation tensor. Just for fun, as one does, let's perform the eigendecomposition of this term. The eigendecomposition will decompose this symmetric matrix into a product of orthogonal eigenvectors stored in V and a diagonal matrix of eigenvalues stored in E. A little bit of rearranging and explicitly expanding our diagonal matrix E gives us the following. The orthogonal matrix V acts as a rotation on delta x, while the eigenvalues of the Cauchy-Green deformation measure how much the object is stretching in each direction encoded in V. Because the Cauchy-Green deformation tensor is a product of a matrix and its transpose, we know that these eigenvalues are really the squared singular values of the matrix, which we can compute by applying the singular value decomposition to the deformation gradient f. If we assume that the material we are simulating is isotropic, that its strain energy density only depends on the total stretch encoded by the singular values, and not in the direction of the stretch encoded in V, we can express our strain energy density as a function of just these singular values, themselves a function of f. In this context, we give these singular values a special name. We call them the principal stretches. This structure often makes it easier to develop new strain energy density functions for simulation. There are really three main criteria that define a well-behaved strain energy density function for elastic objects. Obviously, we would like our elastic cloth to go back to its undeformed shape when we remove all the applied forces. We would like the energy model to be invariant to rigid motions so that translating or rotating the cloth doesn't cause it to deform. And in this particular case, we would like the strain energy density to be computable using position information stored on the vertices of our simulation mesh. Principal stretch formulations are immediately useful because, as we've seen, they filter out rotations by construction. And because they depend directly on the deformation gradient f, they can be computed from the vertex positions of our triangle mesh. What remains is to formulate a strain energy density that ensures that our cloth will go back to its original shape when no forces are exerted on it. Let's build an energy model that does just that, and we're going to make one that's quadratic in the principal stretches. You should be able to convince yourself that this model has a minimum when all principal stretches are equal to 1. Since principal stretches equal to 1 correspond to no deformation, this model satisfies the final criteria of strain energy density. So what does all this mean? Well, this model is measuring two things. The first term measures the 3D stretch or compression of our object, while the second term is measuring the approximate change in volume. This model then tries to balance total deformation while staying close to the volume of the original shape. It's this volume preservation that causes elastic objects to bulge out when we squish them. We control the relative strength of these effects using material parameters called the Lemay parameters. This model is commonly referred to as the co-rotational linearly elastic model. Even though the energy itself is quadratic in the principal stretches, such models often get named for the force displacement relationship they define. This is encoded not by the function itself, but by its gradient, which is linear with respect to our sigmas. Co-rotated linear elasticity is a commonly used model for all sorts of simulation. Let's see if we can get it to work in our cloth simulator. Now that we have a strain energy density function, we can finish building our potential energy. What remains is to compute this integral. Fortunately, our deformation gradient is constant over our triangle, and so is the strain energy density. Integrating a constant function over our element can be done analytically, which leaves us with the following straightforward formula for computing potential energy. Now all that's left to do is to extend this from a single triangle to a whole sheet of cloth. And as is becoming routine now, we compute the full potential energy by summing over all the triangles. As usual, we use selection matrices to connect our global generalized coordinate to the per element energy calculations. So now we've got a kinetic energy, and we've got a potential energy, and we can move on to computing the equations of motion, which starts by computing the Lagrangian. Our Lagrangian is made up of a quadratic kinetic energy and our potential energy. It's structurally identical to what we derived for tetrahedral finite elements. This is comforting since really all we changed was the shape of the element itself. If we plug all this into the Euler-Lagrange equations, we get back our familiar equations of motion, except using our cloth mass matrix and the generalized forces from our co-rotational energy model. Next, we can discuss how to integrate these equations of motion to finally produce some cloth animation. Fabrics like denim or cotton weaves have a high resistance to stretching, and this manifests itself as high forces in our simulation. To handle all of this in a stable fashion, while allowing reasonable time step sizes, we typically use implicit or linearly implicit time integration methods. We've covered such integration schemes in previous videos, and we know that in order to implement them, we will need to be able to compute both the gradient and the Hessian of our potential energy model. Here's our potential energy again, constructed by summing up the potential energy contributions from each triangle. As when computing the tetrahedral finite element generalized forces, we can arrive at a straightforward formula by moving our derivative with respect to the generalized coordinate inside of the summation over all triangles. Applying the chain rule shows us that we can compute the total generalized force on the cloth by computing the per triangle generalized forces and assembling them. Remember to look back at video 4 if you need a refresher on this procedure. Sadly, there are a couple of wrinkles in our specific case of cloth simulation when using principal stretches. Remember that our strain energy density function psi is a function of f via the principal stretches, and these are the singular values of f. This means that we have to perform one more chain rule to arrive at the gradient of psi with respect to f. Here the additional terms come from the singular value decomposition of the deformation gradient. While this step might seem tedious, it actually makes this whole gradient easier to compute, since the derivative of psi with respect to the principal stretches is quite simple. When using implicit integration, we will also need the stiffness matrix for our cloth. And to derive this, we will need to compute the Hessian of the potential energy, which is the sum of the per element Hessian matrices. Taking the required derivatives and applying the chain rule appropriately yields a truly horrible result. In fact, when compared to our volumetric finite element method, a whole extra term has popped up, How did this happen? For tetrahedral finite elements, our world space position was a linear function of our generalized coordinate. This meant that the deformation gradient was also a linear function of the generalized coordinate. The net result of this is that this term was actually zero in the volumetric formulation, and so we never saw it. That's no longer true in the triangular FEM case. Remember that we used the deformed unit surface normal to build a complete volumetric deformation gradient for a triangle. Sadly, the deformed unit surface normal is a nonlinear function in Q. That means that our deformation gradient has a Hessian in terms of Q, which we could compute for the sake of completeness. But before we make the commitment to do that, let's remind ourselves what we use the Hessian for when doing implicit time integration. The Hessian of our energy has a very specific use in Newton's method. We use it to rescale the gradient when we compute the search direction. The Hessian is related to the stiffness matrix by a negative sign. So what is this Hessian doing here? Well, it's just modifying the search direction using local curvature information to, well, hopefully, improve the convergence of our optimization scheme. Do we really need the complete Hessian to do a good job of this? It turns out that the answer is often no. A popular class of algorithms, called quasi-Newton methods, use an approximation of the Hessian rather than the true Hessian inside of the Newton's method. Under a certain set of restrictions, the most important of which is that our approximate Hessian should be symmetric positive definite, we can show that the computed search direction will still be a descent direction. It won't be the true Newton search direction, but it will still be pretty good. For our particular cloth simulation model, we can build a pretty good approximate Hessian by just dropping this second term. This second term is related to the bending stiffness of the cloth, and, at least in what we've discussed so far, we've assumed the cloth has no resistance to bending. That means we don't need to implicitly integrate this portion of the force, and we can safely ignore this contribution to the Hessian. An important note: ignore this term at your own peril if you introduce bending to your cloth energy model. In our particular case, we are left with the usual task of computing the Hessian of the strain energy density with respect to the deformation gradient. Sadly, this is also complicated a bit by the use of the principal strain material. Let's just pull the band-aid off quickly. This scary thing is the formula for the Hessian of a principal strain energy model. Now don't panic, we're going to go through this one step at a time. First and foremost, I want to point out that this subscript ij indicates that we are taking this second derivative with respect to a single scalar value of f at a time. Since the gradient of psi with respect to f is a matrix, this formula can be used to compute 9 separate matrices, the sum total of which constitute a third-order tensor which represents the Hessian. We'll flatten all of this out to a matrix later, like we did in video 4. The matrix delta capital S is just a diagonal matrix of first derivatives, and the vector delta Sij is computed using the following formula. Now this is all just a straightforward consequence of plowing through various differentiations. There are a few terms left undefined here, and to understand where they come from, we need to take a bit of a detour and talk about the derivative of the singular value decomposition. The singular value decomposition of a matrix breaks it up into two matrices of singular vectors, u and v, and a diagonal matrix of scalar values. If we were to change the matrix A, the singular value decomposition output would also change. This means that we can think of the SVD as being parameterized by A. This implies we can compute the effect of a small change in A via differentiation, the basic form of which arises from the chain rule. Here again we write the formula in terms of scalar entries of A. and this simplifies the notation a little bit. Fortunately, there are pretty good off-the-shelf codes to compute this derivative, so for us, it's enough just to understand where it comes from. And we can see the SVD derivative with respect to f popping up throughout this equation. And with that, we have almost all the pieces we need to build the cloth stiffness matrix. We're just missing one thing: the derivative of the deformation gradient with respect to our per element generalized coordinates. We begin with our formula for the 3x3 deformation gradient matrix, but as in video 4, it's more convenient to flatten this out into a vector. We're going to start by defining the 3x3 submatrix D, and then a little fiddling around with the algebra is going to give us something that looks like this, which is the flattened deformation gradient. This shares some similarities with the tetrahedral case. Note the appearance of the B matrix, which contains our shape function gradients, which we store in the D matrix. However, an extra term involving the deformed and undeformed unit normals, n and capital N respectively, has appeared. If we take the derivative of this whole thing with respect to our generalized coordinate, we get the following. Our standard B matrix needs to be combined with a matrix that contains the derivative of the deformed unit normal with respect to the triangle generalized coordinate. Well, why is this term even necessary? Remember that changing our triangle's world space position will naturally change the orientation of the surface normal, and we have to account for this correctly in our calculations. We can define the unit surface normal as the normalized cross product of triangle edge vectors. These edge vectors are in turn related to the generalized coordinates of the triangle. We can now use our friend the chain rule to estimate the effect of tiny changes in the triangle configuration on the surface normal. This equation looks a bit scary, but it's pretty easy to evaluate, and it has a nice intuitive meaning. This gradient matrix estimates the infinitesimal rotation induced in the triangle and then projects out any component that is attempting to change the length of the normal. We'll call this whole caboodle nu for brevity's sake. Using nu, we get a concise definition of the deformation gradient derivative with respect to the local generalized coordinate, and we can use this to compute all our potential energy gradients and Hessians. Which means we can finally simulate this full piece of cloth. Let's sit back and take a second to appreciate all of our hard work. Well, maybe there's still a little bit more work to do, because you can see something happening in this animation that we haven't talked about before. Contact. Our cloth is colliding with a sphere. Now it turns out we can use a pretty simple approach to add this feature to our cloth simulation. So let's see how. Typically in simulation, algorithms for handling collision are divided into two phases: collision detection and collision response. Collision detection detects collision between objects, while collision response decides how to alter the motion of the objects involved in the collision to resolve the contact. Our case study will be a cloth collision with a sphere, and we'll focus on one per vertex collision detection and response. Let's get right to it, starting with collision detection. Collision detection with a sphere is pretty simple. We just need to check if the distance between our vertex and the center of the sphere is less than the radius of the sphere. If it is, a collision is occurring. Typically, we work with squared distances to avoid irritating squared root calculations. Once we have identified that a point is colliding with the sphere, we have to figure out what to do about it. Now, this decision will be based on not just the position of the point, but also its velocity. Our collision response will be built around the principle of not making things any worse. And another way to say that is if our vertex is colliding with the sphere and its velocity is moving into the sphere, well, it should stop doing that. Defining movement relative to the sphere can be done using the sphere's outward-facing surface normal at the contact point. Specifically, we can attempt to remove any component of the cloth velocity that's moving opposite the sphere normal. Such approaches are called velocity filters because they filter out offending components of an object's velocity in order to resolve collisions. Mathematically, we can formalize this by specifying that our filtered velocity will be our original velocity plus a perturbation along the sphere normal. We know that our filtered velocity should be moving away from the sphere, or that the projection of the final velocity onto the sphere normal should be greater than or equal to 0. Using these two equations, we can come up with a bound on alpha. However, there's a problem here. There's really a lot of alpha values that meet this criteria. So we need some additional information to narrow our choice down to a specific value. Let's introduce two common sense notions that will help us do this. First, let's aim to change the velocity of the vertex as little as possible. Second, if the vertex velocity is already taking the vertex away from the sphere, we shouldn't interfere with that. We should do nothing. This if statement implements exactly these two rules. Here, if the velocity projected onto the sphere normal is positive, the vertex is moving away from the sphere, and we don't need to change the velocity, so we set alpha to 0. Otherwise, we need to remove just the component of the velocity moving into the sphere, and we can do this by removing exactly the projection of the velocity onto the normal, or setting alpha to its lowest bound. Conveniently, this whole if block can be condensed into a single minimum operation. And this yields the final collision resolution algorithm. For each vertex, we check if it's colliding with the sphere. If it is, we compute the velocity projection onto the sphere normal at the contact point, and use this to compute alpha and update the velocity. And that's it. Now we can resolve collisions between our cloth and a sphere. And you now know everything you need to know in order to build a cloth simulator with simple collisions. And now we come to a very important point in this video series, because this cloth simulation will be the last time that we talk about deformable elastic objects. The next few videos are going to focus on one of the most wildly popular and impactful applications of physics-based animation in industry, games, and much further than that. And that's rigid body simulation. We're going to learn about rigid body mechanics, how to simulate joints between rigid bodies, and rigid body contact. So really lots of fascinating stuff coming up. Once again, thanks for watching, and hopefully I'll see you back next time.